All right, let's get into something really cool. We are right on the edge of having AI that can actually navigate and interact with our physical world, in things like robotics or self-driving cars. But for any of that to happen, AI has to master a really basic skill: understanding 3D space. And today, we're looking at what might be a massive breakthrough in how AI learns to do exactly that.
You see, for an AI to be truly intelligent, especially out here in the real world, it can't just be about processing text or flat images. It has to be able to see and reason about complex, three-dimensional scenes. This is what's known as spatial reasoning, and it's the absolute bedrock of what researchers call embodied intelligence. Basically, AI that can use a physical body, like a robot, to interact with its surroundings.
So, if this is so incredibly important, why don't we have robots flawlessly navigating our homes already? What's the major hurdle? What's the one thing that's preventing this giant leap forward?
Well, it turns out the whole problem really comes down to the training. Teaching an AI to see and actually understand the geometry of the world around it is without a doubt one of the biggest challenges in the entire field today.
And why is it so hard? Because of a gigantic data bottleneck. I mean, think about it. To teach an AI about 3D space, you need just unimaginable amounts of data, where every single point, every object is painstakingly labeled. This process, called geometric annotation, has always relied on just a staggering amount of human labor, which means it costs a ton of time and, you guessed it, a ton of money.
So this huge bottleneck has kind of forced researchers down a couple of different paths for training AI. But as we're about to see, both of the old ways have some really serious flaws.
The first, and honestly the most common approach, is to just throw people at the problem. You literally hire teams of human annotators to go through and create these massive, meticulously labeled datasets of 3D environments. Now, I absolutely love this metaphor that the researchers use in the paper. They describe this whole process as being like carving ice cubes from a glacier. It's incredibly slow, it's unbelievably expensive, and maybe worst of all, what you get at the end is a static, frozen dataset. It can't adapt, it can't change as the model gets smarter. It's just stuck.
So you've got these two main camps, right? On one side, you have these static datasets. Yeah, they're accurate because humans check them, but they're rigid and just don't scale. And on the other side, you have this idea of a self-evolving AI, one that generates its own training data. It sounds awesome in theory, but it has a pretty fatal flaw. And this is that flaw. Think about it. If an AI is making up its own questions and its own answers, how does it ever know if it's right? The usual method is to rely on what's called model consensus. Basically, the AI just trusts its own best guess. And this creates a super dangerous feedback loop, a total echo chamber where the AI's own mistakes and misunderstandings just get reinforced and amplified over and over again.
But what if you didn't need human labels? And what if you didn't need to rely on the AI's own flawed consensus? What if there was a way to find the absolute 100% undeniable truth without either of them? Well, this is where the story gets really good.
The researchers behind SpatialEvo had this absolutely brilliant insight. See, unlike labeling a photo and arguing if it's a cat or a weird-looking dog, 3D geometry isn't subjective. It's governed by the laws of physics and math. When you have a 3D scan of a room, the relationships between objects aren't a matter of opinion. They are a computable, verifiable fact.
And this quote from the paper just nails it. The ground truth, the right answer, can be calculated directly from the raw data itself. You don't need a person or an AI to guess the answer. You can mathematically derive it with perfect accuracy. It's already there.
So building on top of this powerful idea, the team created a whole new framework for teaching spatial intelligence, and they call it SpatialEvo. So we are moving away from that slow, static ice cube factory on the left, and we're moving toward a dynamic, self-correcting, self-improving learning engine on the right. This is a system that literally creates its own curriculum and then checks its own work against mathematical certainty. Now, the absolute heart of this engine is something they call the Deterministic Geometric Environment, or DGE. Their best way to think of it is like a perfect, totally impartial referee, or maybe a geometric oracle. It can take any 3D scene and instantly turn it into this interactive world where any spatial question can be answered with zero noise, totally objective feedback. So, how does it all work? It's actually this super elegant learning loop. Step 1. An AI agent called the questioner looks at a scene and comes up with a brand new, physically valid question. Step 2. Another agent, the solver, does its best to answer it. Step 3, and this is the magic part, the DGE verifies the answer against that absolute, calculated ground truth. And finally, Step 4, the model learns from that perfect, error-free feedback. It's brilliant.
And it gets even smarter. The system also has a task-adaptive scheduler. What that means is it automatically figures out where the AI is weakest and focuses the training right there. It creates this personalized, dynamic curriculum completely on the fly, with zero human supervision needed.
Okay, so all of this sounds incredible in theory, right? An automated, self-improving system for learning 3D space. But the real question, the one you're probably asking is, does it actually work?
Oh, it works. The results are, frankly, pretty staggering. When they put it to the test, SpatialEvo got the highest average score across 9 different spatial reasoning benchmarks. And this wasn't just for one size of model. It came out on top at both the 3 billion and the 7 billion parameter scales.
So here's the bottom line. The system consistently gets better at its main job, spatial reasoning. And what's really critical is that it does this without getting worse at other general vision tasks. But most importantly, it shows us a clear path forward for scaling up AI intelligence without being held back by the insane cost of human data labeling.
And this leaves us with a really fascinating final thought. SpatialEvo basically proves that for certain types of problems, we can completely replace expensive, sometimes subjective human labels with objective, computable truth. It really makes you wonder, what other complex skills out there are secretly governed by deterministic rules, just waiting for someone to have a similar breakthrough?